Hello, welcome to the final part of economic feasibility assessment. In the previous three parts, you have learned present worth, annual equivalence, and the rate of return analysis. In this part, we will explore the benefit-cost analysis, which is commonly used in evaluating public investment. An essential aspect of evaluating public projects is quantifying their benefit in financial terms. For example, in airport runway expansion, what are the economic benefits of reducing airport delays? From the airline's point of view, taxing and arrival delays means added fuel cost. From the airport's point of view, delays means lost revenue in landing and the departure fees. From the public point of view, delays means lost earning, as people spend more time traveling and less time earning a living. To assess whether the public investment in such a project is justified, we employ a method known as benefit-cost analysis. This analysis compares the total cost of the project against the quantified benefit to determine the financial viability. Similar to profitability analysis in the private sector, benefit-cost analysis helps policymakers ensure that the public funds are used effectively to yield the tangible economic advantage. Benefit-cost analysis is the systematic approach used to evaluate outcomes of projects by comparing their cost to their benefit. This analysis can serve multiple objectives. First, maximizing benefit. The primary goal is to achieve the highest possible benefit for any given set of cost or budget. This ensures efficient use of resources. The second, maximizing net benefit. When both benefits and cost can vary, the objective shifts to maximizing net benefit, which is the difference between the total benefit and the total cost. The third, minimizing cost. For the predetermined level of desired benefit, the aim is to minimize the cost, enhancing cost effectiveness. It is crucial to understand that the goal of cost-effectiveness analysis, which often complement benefit-cost analysis, is not just about finding the least expensive option. Instead, it is about assessing whether the additional benefit of more costly option justify the actual expenses. Additionally, a key distinction between cost-effectiveness analysis and the cost-benefit analysis is that the former include evaluation that might not be strictly monetary. This evaluation might assess the social impact, which can be categorized as significant, moderate, or minor, and factor this into the decision-making process. Now let's break down the process of conducting the benefit-cost analysis into three structural steps. First step is to identify user benefit, including assess all direct and indirect benefit to users in monetary terms, identify any possible negative impact in dollar terms, and then subtract this benefit from benefit to determine the net benefits to users. For the second step is to identify the sponsor's cost, such as initial capital expenditure and any residual value at the project ends. Account for ongoing operating maintenance and the renovation cost, and estimate annual revenue, such as tolls or service fees generated by the projects. Finally, calculate sponsor's costs by adding non-recurring and the recurring cost, and then subtract the generated revenues. For the third step, the final step, is to perform the benefit-cost analysis, which include choose an appropriate discount rate for the analysis, calculate the present value of the net benefit, and the all cost over the project lifespan, and then divide the net benefit by the sponsor cost to determine the benefit cost ratio, or BC ratio. Accept the project if the BC ratio is greater than 1, meaning the equivalent user's net benefit exceeds the equivalent sponsor's net cost. In evaluating public projects, it is important to note that the interest rate used is often referred to as the social discount rate. This rate serves as the critical tool for government to assess the viability of public investment. Typically, state and city government may adopt the social discount rate that vary from those used by the federal government, generally ranging from 3% to 8%. The specific rate chosen depends on the project nature and the economic outcomes that it aims to achieve. So in this exercise, we will explore how to compute the BC ratio using a hypothetical project scenario. So project cash flow are shown as this slide. For initial investment, $10 at year 0, followed by another 10 at the year 1. For recurring costs occur annually from year 1 through year 5, starting at $5 and increasing to $8 in the year 4. And for benefit, starting from year 2, the project generates $20 annually, increasing to $30 in year 3 and year 4. And for salvage value, an additional $5 benefit will occur in year 5. So to solve that, first we calculate the present value of the total benefits by discounting future cash inflows to their present worth, which sum up to $72. And next, we calculate the total cost, which include the initial investment and the recurring cost, all discounted to their present value, and then sum them up will give you around $34. Finally, we calculate the BC ratio by dividing the total benefit by the total cost, which is 2.1. Since the BC ratio is greater than 1, the project is considered economically viable as the benefit exceeds the cost. In our previous part, when we discussed rate of return ROR analysis, we emphasized the importance of using an incremental investment approach when comparing the different mutually exclusive project alternatives. This method is equally crucial in benefit cost analysis, since the BC ratio is also a relative measure. Here's how we apply the incremental BC ratio analysis. First, we begin by eliminating any project option with a BC ratio less than 1, because these are not economic viable, right? Then we arrange the remaining alternatives in increasing order based on their cost. This helped in comparing each progressively more expensive option against the cheaper one. And next, for each pair of alternatives, compute the differences in benefits and cost. For each pair, like J and K, where J is the less expensive alternative compared to K, calculate the incremental benefit cost ratio. Such ratio will tell you how much additional benefit will be gained per unit of additional cost. If incremental BC ratio for the pair is greater than 1, the more expensive alternative, like K, is justified and should be considered over the less expensive one, J. If not, retain the less expensive option, and then continue the process through the list of alternatives. The final alternative selected in the last pairing comparison is determined to be the most cost-effective choice among the all considered options. So let's consider the 3 investment projects, A1, A2, and A3, all three projects offer the same service life, and we have calculated the present worth of each project component at a 10% discount rate, as shown in this table. Here comes two questions. First, if all three projects are independent, which project would be selected based on the BC ratio? The second question is that if the projects are mutually exclusive, which one would be the best one? To solve that, for part A, we need to calculate the BC ratio by dividing the benefits by the cost for each project. And we found out that all BC values are higher than 1 in this example. That means all of them are acceptable, given they are independent. Here, we can also observe that using the BC ratio criteria will lead to the same conclusion about the accept or reject as under the PW or present worth criteria. For part B, we need to determine the best project to undertake. We will use an incremental analysis approach. We'll compare a project by incrementally analyzing the additional cost and benefit of one project over another to ensure we select the project that maximizes the net benefit relative to additional cost. So in this example, we first arrange the project by increasing order of the denominator C for the BC criteria. We then compare the project incrementally. First is A1 versus A3. The incremental BC ratio is computed to be 1.5, which is greater than 1. So we prefer A3 over A1, right? And next, we must determine whether the incremental benefit to be realized from A2 would justify the additional expenditure. Therefore, we need to compare the A2 and A3. The incremental BC ratio again is greater than 1. Therefore, we prefer A2 over A3. With no further project to consider, A2 becomes the ultimate choice. One of the key takeaways here is that by computing the incremental BC ratio, we ultimately will select the project that is consistent with the PW or present worth criteria, which is project A2 in this example. Okay, that wraps up our exploration of the benefit-cost ratio analysis, which marked the conclusion of our economic feasibility assessment unit. I hope you all have gained a comprehensive understanding of how the different types of analysis can serve as the crucial tools for evaluating the financial viability and the potential impact of different projects. They are all vital for making informed decisions, especially when resources are limited and investment impact are significant. As you move forward, keep in mind how these principles apply not only in theoretical scenarios, but also in real-world engineering applications, which may further shape the way government, business, and organizations allocate resources and prioritize projects. See you in the next unit. Bye-bye.